Last unit, I talked about the forces that a charged particle would experience because of a magnetic force. Because of a magnetic field. And again, the charged particle had to be moving. This is going to talk about the source of that magnetic field. A current-carrying wire can not only experience a force if it's placed in the magnetic field, but also it creates a magnetic field around it. And the magnitude of that magnetic field is this Biot-Savart law, which should be on your formula sheet. I do not expect y'all to memorize it. The rules. So the magnetic field that's created by a current-carrying wire will be perpendicular to the current and to the radius. So in other words, if you have this current-carrying wire here and the radius is from here to there, the magnetic field is out of the page or into the page. It's going to go around the wire, which is perpendicular to both the current and the radius. It's inversely proportional to r squared, so again, it's got that 1 over r squared relationship. It's proportional to the current, and it's proportional to the angle between them because it has to be perpendicular. So again, over the r squared relationship, and we've got a constant I ds cross r. So here's the right-hand rule for that. If the currents go in this direction, the magnetic field that's created by that, not experienced by the wire, but created by the wire, is going in the direction that your fingers would run around it. And we will go through and do some of those. I'll make sure I do some of those, probably on paper, and hand them to you. All right, if you have two current-carrying wires, then there's a force which has a magnitude of force per unit length of mu O over 2 pi A times I1 times I2. Again, it's based on the current of both. If the currents are moving the same direction, then the force will be an attractive force. And if the currents are moving in opposite directions, then the force is a repulsive force. And then the last little bit for magnetism is Ampere's law. Let's see, where are my notes? Here we go. Ampere's law, well, we've got Ampere's law and then Gauss's law. But Ampere's law says that the total of the magnetic field around any closed path is equal to mu O times the current through that path. So the line integral around any closed path equals mu O I, where I is the steady current passing through any surface bounded by the closed path. So if I put a circle around those two wires, notice this one's going out of the page, this one's going into the page, that one's going out of the page as well. Between these two, there's a total magnetic field for that path. Inside that path would be, well, along that path is equal to 1 amp out of the page. Along this path is 6 amps. Along this path is 3 amps. This whole path, path A, would be 1 plus 6, okay, would be 4 amps. And if y'all want to go look at your book, I mean, it goes through all those. Which means, for a wire, the total magnetic field inside the wire is proportional to the amount of charge, amount of current inside that wire. But then as you move away, it's got that 1 over R relationship. For a toroid, you get a magnetic field along this line, like inside the toroid, but not really much outside. There's a slight one outside, but nothing that we're going to work with. And the magnitude of that magnetic field inside a toroid is mu O Ni over 2 pi R. This N is the number of loops around that toroid. So it's the same equation, we just added this number of loops there. Whereas this one was just mu I, where is it? Mu I over 2 pi r was what it would be for this, because this path is 2 pi r. And then for a toroid, you multiply it by the number of loops, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, so 22 to maybe 23 for this one. All right, for a solenoid, which is just a straight helical wire that's coiled like that, solenoids will develop a magnetic field that looks very similar to a bar magnet, coming out one end and then to the other end, and you can establish that by just doing right-hand rule with your wire here. And the magnitude of that magnetic field is mu o I over, like, times n, because there were n loops, depending on how this would be 1, 2, 3, 4. That would be 4. And then instead of 2 pi r, this is just L, length of L. So again, it's still dealing with that Ampere's law like formula. And then finally, Gauss's law for magnetism. Gauss's law says that the total flux through any enclosed surface is equal to the integral of B dot dA. It's very similar to what we saw for Gauss's law for electric fields. The distinction is, for Gauss's law for electric fields, the total electric flux was equal to Q inside over E naught. The total flux inside a enclosed surface in terms of magnetic flux will always be 0, because you can never have a magnetic monopole. So again, here is, like, through this, which is an electric, you were looking at the electric flux, the total electric flux would be QO, the charge of the electron, divided by mu naught. Whereas here, the total magnetic flux around this area is 0. Magnetic flux through any closed surface is always 0, no matter what. I want y'all to be familiar with the definitions ferromagnetism, paramagnetism, and diamagnetism. So ferromagnetic substances, you can develop a permanent magnet with those. If you place them in a magnetic field, the atoms like permanently align, and then they stay that way. If you have a paramagnetic substance, these objects will they will align in the presence of a magnetic field, but then if they're removed from that magnetic field, that lining up competes with just the random motion of the electrons, and so it goes back to non-magnetic. It's not a permanent magnet, in other words. It can develop a magnetism in a magnetic field if it's paramagnetic, but it will not become a permanent magnet. And then diamagnetic will actually have a magnetic moment in the opposite direction, so they actually are repelled in the presence of a magnetic field. And I think that's it. Okay, so here is flux. Again, it's 0 for any enclosed surface, magnetic flux. This is the Biot-Savart law, which is the magnetic field created by a current carrying wire. This would be 2 parallel wires. You might want to look and see which ones of these are on your formula sheet. And then Ampere's law says that the total magnetic field around any path, not enclosed surface, but any enclosed path, is equal to mu O times the current in that path. And so this is for current carrying wire, the same thing for a toroid, and that's for a solenoid. Those are all applications of that same formula right there. So if you can get the Biot-Savart law, Ampere's law, then you could determine these. This around a current carrying wire is a circle, right? It's a sphere, you just cylinder there. For this one, around a toroid, it was also a circle, but there were in loops. And around a solenoid, it's just the length of the solenoid. We just did that, Gauss's law of magnetism, and then here are the definitions of those three types of materials. Diamagnetic, in which the magnetic moment is weak and opposes an applied magnetic field. Paramagnetic, magnetic moment is weak and in the same direction. And then ferromagnetic, the magnetic moment will be permanent, basically. I want y'all to know those three. Okay, and I think that's it for magnetism, and I will get y'all one more video on induction, and that will be the end of the electromagnetic notes. I will go through and work some of the problems, but I'll probably do that on paper so I can write out some notes for y'all. But I've got one more on inductance, maybe two more, we'll see. Well, let's see if I can, there we go.